go to do a little screencast and talk about sort of all of motion that we've covered so far, or that you've learned about in the CK12 assignments, but especially talk about this most recent assignment where you're trying to find displacement and acceleration, and some of those equations are really hard. So I thought it would be a good idea, since we're not Zooming this week, and since my Wi-Fi wasn't working when we were Zooming, that I can sort of talk about it here. All right. So if we look, and this is my iPad on my computer screen, this is the motion study guide from CK12, right? So if you need help finding this, you can let me know. But these are really good, that after each unit you're covering, or during each unit, you can look back at these study guides that show you sort of a little bit of everything that the textbook covers. So it has some things that we already know, right? Some key terms. We talked about displacement, speed, velocity, learning about acceleration now. We're not going to talk about projectile motion in here, and we will probably talk about free fall later. So this will be later. So it gives the definitions, the units, which are helpful right up here. It also gives some more notes on displacement versus distance, which we did, speed versus velocity, which we did, acceleration, which we're doing now, right up here. It talks about a couple things here that we haven't gotten to yet, or maybe won't talk about this year, but they're still good to know, so you can take a look at some of these things. But we did talk a lot about this already in the last Zoom, if you were there, and I'm sure you've probably seen it in the textbook as well. All right, and then a couple more vocab words, which, again, I think I talked about in the Zoom if you were on it, but instantaneous velocity versus average velocity, and acceleration and speed, all that stuff. Just a couple more vocab words. All right, we're going to talk about graphs later, so this is another one that'll come later. So we don't worry about that right now. We're not doing this. Okay, this is the part that I wanted to have open for this screencast. These are our equations over here and our variables over here. These are all the things that we can measure. This really should be, a couple notes here, this should be change in x, means displacement. X is just position. So my change in position is my displacement. This doesn't really matter, but a lot of times I'll write, for whatever my velocity is right now, I'll write velocity final, like after some sort of speeding up or slowing down. These two are examples of instantaneous velocities. Right now, or right now. What's my velocity? Right before I sped up, or right after I slowed down, or whatever. Also, for initial velocity, a lot of times you'll see me also write VI. They write V0 as like the kind of almost like, I don't know. It's a common notation for initial, but I might write VI. It means the same thing. Okay, if we look over here, we've already seen some of these equations and these relationships. This is like my average speed equals distance over time equation up here, just with vectors instead of scalars. So my average velocity for like an entire trip, so this is not an instantaneous number, this is an average. So for an entire trip, if I go this far in this amount of time, I can figure out this is my average speed. I could also rearrange this any way I wanted to. Right, if I multiply both sides by change in t, my average velocity, which a bar above the number or above the variable means average as well. Average velocity times the time it took to do that, go that speed or that average velocity, is how far I go. And I could solve for change in time as well. If I divide that by velocity, I get t equals how far I go divided by my average velocity. So I can rearrange that however way I want. All three of these are the same equation. 1, 2, 3, they're all the same equation. Just same relationship, just in different orientations. All right, then we learned about this one. What does average acceleration mean? Acceleration, we don't really need the word average here. I'll usually just write it as acceleration because we're never going to have a time where we change my acceleration. I might change my speed, but I'm never going to change my rate of acceleration. So my average acceleration, though, equals change in velocity over change in time. So however, the rate, that's what change in t is, the rate of my change in velocity. Some sort of speeding up, slowing down, or turning, which we don't ever do the calculations with turning, but another way to write change in velocity is v final minus v initial. And I can write either I or 0 for initial. Right, so v final minus v initial over the time it takes to do that change, that's my acceleration. One thing that's kind of weird that they put a second equation here is if we look at this equation here, it's the same thing as the one above, just rearranged. So I could prove that to you right if I subtract v0 from both sides, minus v0, and then divide both sides by t, I get this same thing up here. So this equation is certainly helpful for finding maybe a final velocity if something's accelerating for a certain amount of time. Maybe it started from rest, which means this is 0. A lot of times things start from rest. That means they're not moving to start. So this equation certainly can be helpful. However, we don't really need it because it is technically the same as this one. So anyway, those are the top 3 equations which we should be able to picture kind of what they're telling us or what relationships they're showing us. These two are a lot harder. All right, we can't just look at them and say, okay, I can kind of see the relationship that it's trying to describe. In this video, a lot of what I'm going to do is I'm going to try to explain this equation here. Maybe not every single component of that equation, but I'll at least show you how we get that, why we need that equation. This one, I'm not really going to describe. It's really hard to picture what that's telling us. However, I will post another video that shows we don't need to know how we get this equation, but we can know how to use it. And I'll talk about that a little later, but we can still use this tool here, this relationship, this equation down here. Even if we don't know what it really means, we can still, okay, we know that's true, that the final velocity squared equals the initial velocity squared plus 2 times the acceleration times displacement. We don't need to understand what's happening there, but we can at least use that to solve for one of those 3, and I'll talk about that later, or one of those 4. All right, so let's get to this equation right here. If we notice from these 2 equations, oh, Russell's crying. Sorry, Russell. If we look at these 2 equations up here, there's no variable in there. There's no displacement. Meaning if we only knew the definition of acceleration and like how fast it's going, these 2 equations, which is really just one equation, but we can't figure out how far something goes if we just know, okay, the acceleration is maybe 2 meters per second squared, which means it gets 2 meters per second faster every second, or maybe slower, but and then maybe it's accelerating for 4 seconds. Nothing up here tells us how far it's gone. Now you might think, all right, well, maybe it starts from rest here. Maybe I can say, all right, well, if it's accelerating at 2 meters per second squared for 4 seconds, that means the velocity at the end, its final velocity, is 8 meters per second. It's getting 2 meters per second faster times 4 seconds that it's doing that. So the final velocity is 8 meters per second. And maybe you say, all right, well, 8 meters per second, let's go to this one, 8 meters per second times 4 seconds. Yep, that's how long it was going. And I can figure out how far it was going. But this 8 meters per second down here is not my average velocity. I'm not averaging traveling 8 meters per second that entire time. That's just how fast I was going at the end. If I wanted to figure out how far I was going, or how far I have gone, my displacement, I have to plug in the average velocity, which, as it turns out, is always halfway between the initial and the final velocity, as long as acceleration is constant, which all of these equations only work if acceleration is constant. Again, that's different than constant velocity. I know it's kind of tricky, but so what I would end up doing is say, all right, if I plug it into this equation up here, I'll just bring that down here. I know there's not a lot of room here. My average velocity equals, my average velocity times time is how far I go. All right, well, if I plug some of these in, my average velocity isn't 8. My average velocity is halfway between these two, which is 4, times my 4 seconds is 16 meters. Now we can do that every single time we want to figure out how far something goes, but we had to use 2 equations. We had to use, let me erase a bunch of this. It's getting annoying. All right. I had to use 2 equations. I had to use this one. Well, I had to use this one first, and then I had to use this one up here. Right? So every single time I have to use 2 steps, 2 equations to figure out how far something goes if I just have its acceleration and how long it's accelerating for, and maybe how fast it was going to start. What we can do, basically what people did, somebody before me, basically rearranged these 2 equations, and really there's a third equation, which is that the average velocity is always right in between those 2. They combined those 2, or 3, and they just made 1. And the way we do this is if instead of doing 3 steps, right, 1 to find the final velocity, 1 to say, all right, the average velocity is halfway in between those, and then the other one here, that's kind of confusing. We can just do that in 1 step. Remember, our displacement was 16 meters. So let's get back to here. This is what we are given in the problem. There's some problem somewhere that says the acceleration is 2 meters per second squared, the time is 4 seconds, and technically I should have a direction on here, but we're not going to worry about that right now, like plus or minus or something like that. But okay, I'm given these 3 things, and I'm looking for how far it goes. I'll write that. I can look at this list right here and say, all right, well, I'm just going to look at that list and decide which equation I can use that has all 4 of these things in it. It has the 3 things I'm given and the thing I'm looking for. So I can just plug in 3 things and then solve for the 4th. So let's try that. If I look, this equation has all 4 of those things in it, all 4 of these variables, but no others. So I can choose that equation. So let's say let's say I do that down here again. Again, not a lot of room, but my displacement is going to be how far I go. I just plug them into this equation. So my initial velocity is 0 times 4 seconds plus 1/2 times 2 meters per second squared times 4 seconds squared. And so this plus this, we got to remember order of operations. Well, 0 times anything is just 0. 1/2 times 2 is 1, times 4 squared is 16. So how far I went? I went 16 meters. It works the same. A lot of times you might see, I think it was in the textbook page, but a lot of times we start from rest, so this is 0. So you might just see an equation that has 1/2 at squared, it comes from this equation just if we're starting from rest. That's 0. All right. I have this simulation thing, which you guys can't use on your iPads because it's Java, but we can use it here. So let's try this problem that we just did and plug in all of the things that we know to start, and then I'll press play and play it for 4 seconds. Okay, so we know that the acceleration was positive 2 meters per second squared. So you'll notice the guy's going to get faster by 2 meters per second every second. If you watch this number, his velocity, this guy will get faster, 2 meters per second faster every second that ticks off. So at 1 second, this will say 2. At 2 seconds, this will say 4. The position, though, it's not like he's going to go 2 meters farther every second. If we watch this guy, he's going to go a little bit of distance or displacement the first second, then a little farther the next second, then even farther the next second. This is why we can't just like multiply this 2 times the time, because that he's not going 2 meters every second if we want to know how far he goes. All right, so his initial velocity is 0. What else do we know over here? And I'm just going to hit play for 4 seconds and see how far he goes. So let's see how close we got. We think he's going to go 16 meters. So let's see if I push play. Go for 4 seconds. 3.5. This is a little. All right. I went a little over 4 seconds. Position was 17 meters, but that's still pretty close. Let me try again. See if I can get exactly 4 seconds. I wish you could program it to say just run 4 seconds. But anyway, I'll push play. 1, 2. There it is. 4 seconds. And this says basically 0.7. So we can figure out using this equation how far it goes when it's accelerating, or displacement. If we look at this equation, it's quadratic, which kind of makes sense. So if let me do this, I'm going to go down here and add a page. Nope, that's not how I add a page. How do I add a page? Yeah. Really? All right. Clearly, I don't know how to add a page. But anyway, let me go to just a new note. Get out of here. All right. Anyway, just watch me fumble around on here. So let's restart. My computer's freezing a little bit. All right. All right. So let's say the person is accelerating at 2 meters per second squared. Over here, this is not. I'm going to sort of look at where this person is going to move like this. He's going to move a little bit and a little more because he's going faster. Right? When you're accelerating, you're going faster and faster and faster. So his sort of This is not working. No, this one's frozen. All right, that's fine. Anyway, I think you guys might get it a little bit more than before. So I can't do the next thing I was planning, but we can look at that equation. How far he goes equals 1/2 AT squared is quadratic. If I plot, and we're going to look at graphs later, but I can show you now. If if I look at these graphs, if he's accelerating at 2 meters per second squared, that means he's going to get 2 meters per second faster each second. So his velocity would be 2 meters per second. Each second it goes by, it's going to be 2 meters per second faster. So this is just going to be a line right here that gets with a slope of 2, because he's getting 2 meters per second faster each second. But this one, he's not going 2 meters farther each second. He's going farther and farther and farther, and it's going to be quadratic. He goes a little bit in the first second, then a little farther, and then farther in the next second, and then farther in the next second, right? And it's quadratic, and then he hit the wall. So that equation for that graph, that line, that parabola, would be 1/2 AT squared. Anything that's accelerating makes a parabola on this type of graph when you're graphing where he is and how far he's gone. But it's a line on the velocity because he's changing his velocity. All right, this may have been a lot. Hopefully it helped and didn't hurt. I will post another video on sort of how to use those equations that we saw. I know I talked about it a little bit. I'll post another one. This is really tricky when we get into this quadratic here and how far something goes when it's accelerating, and those funky equations with either one variable squared or another one squared, right? We can't just decide whether to multiply two numbers or divide. We need to actually look at the relationship between how far something goes and its acceleration, which is not just multiplying the two numbers together. Anyway, I hope this helped. We'll do some more of this moving man, and I'll do some more screencasts if this helps later when we talk about motion, which might be next week, I think. But anyway, have a good long weekend, and I'll talk to you guys later.